Previously, we covered the core foundations. Now in part 7, we tackle Mars, exploration and open questions. Mars has been studied up close for over 60 years, and we still can't answer the most fundamental question about it. That question shapes everything: how we read its rocks, why space agencies keep sending missions there, and what we're actually hoping to find. Last episode, we looked at Mars's moons, Phobos and Deimos, and how their origins remain genuinely uncertain. This episode is about the planet itself as a target for science. What decades of exploration have revealed, what the geology and climate tell us, and why the question of life, past or present, is still open. That last point matters right now, because we have active missions on the surface and in orbit, returning data that's actively changing the picture. So here's the core question: has Mars ever had the conditions to support life? And if so, where is the evidence? Let's start at the beginning. Mars sits at an average distance of roughly 228 million kilometers from the Sun, about 1.5 times further out than Earth. One Martian year runs to 687 Earth days. Its axial tilt is 25 degrees, close to Earth's 23, which means it has seasons. That detail matters more than it might seem, and we'll come back to it. The planet is small. Diameter just over 6,770 kilometers, a little over half of Earth's. Surface gravity is about 38% of what you'd feel here. The atmosphere is thin, surface pressure less than 1% of Earth's, composed mostly of carbon dioxide, with traces of nitrogen and argon. Average surface temperatures sit around -60 degrees Celsius, though they swing dramatically depending on latitude, altitude, and season. None of that sounds particularly promising for life. But Mars has a history, and that history is the whole point. Here's the first open loop. Early Mars was a radically different place. The evidence is written into the surface. The question is how different, and for how long. The oldest terrains on Mars, the southern highlands, are heavily cratered and date back more than 3.5 billion years. Scattered across them are features that look unmistakably like ancient river valleys, lake basins, and deltas. Jezero Crater, where Perseverance landed in February 2021, was once a lake fed by at least one river system. The delta deposit at its western edge is visible from orbit and confirmed on the ground. Water was there, liquid water on the surface for long enough to carve valleys and deposit sediment. That's established science. What we don't know is how long the wet period lasted, or whether it was one continuous era or a series of shorter episodes separated by cold, dry intervals. Some models suggest a warm, wet, early Mars, persisting for hundreds of millions of years. Others point to something more episodic, driven by volcanic activity, large impacts, or shifts in Mars's axial tilt, which is known to vary far more wildly than Earth's over geological time. Mars lacks a large stabilizing moon like ours, so its tilt has probably wandered considerably over billions of years, driving dramatic climate swings in the process. That's why the axial tilt point matters. When the tilt was higher, ice currently sitting at the poles would have migrated toward lower latitudes. When it was lower, it would have concentrated back at the poles. Those cycles moved water around the planet over millions of years, potentially creating habitable zones that shifted as the climate shifted. Which brings us to the exploration record, and this is where it gets genuinely impressive. Spacecraft have been visiting Mars since the 1960s. The early missions were flybys. Mariner 4, which flew past in July 1965, returned 22 grainy images, enough to show a cratered, apparently dead world. Every mission since has chipped away at that picture. Orbiters have now mapped the surface in extraordinary detail. Mars Reconnaissance Orbiter, which arrived in March 2006, carries a camera capable of resolving objects less than 30 centimeters across. It's returned more data than all other Mars missions combined, and it's still operating. On the surface, the rover record stands on its own. Spirit and Opportunity landed in January 2004. Opportunity ran for nearly 15 years before a dust storm ended its mission in June 2018. It drove over 45 kilometers and found mineralogical evidence, hematite and sulfate deposits in particular, consistent with prolonged exposure to liquid water. Curiosity has been working Gale Crater since August 2012. It found organic molecules preserved in mudstone, and evidence that the crater once held a lake with chemistry that wouldn't have been hostile to microbial life by Earth standards. That's a precise and important statement. It's not evidence of life. It's evidence of habitability. Perseverance has gone further still. It's actively collecting rock core samples intended for return to Earth, the first step in a joint NASA-ESA sample return mission. If those samples arrive in the early 2030s as currently planned, they'll be subjected to laboratory analysis that no rover instrument can come close to matching. Here's the second open loop. We found the right conditions, repeatedly, in the geological record. The question is whether biology ever took advantage of them. That question is genuinely open. There's no confirmed detection of life on Mars, past or present. The Viking landers in the 1970s ran biology experiments, and the results were ambiguous enough to be debated for decades. The current scientific consensus is that Viking didn't detect life, but those experiments weren't designed to be definitive, and our understanding of Martian chemistry has changed considerably since then. What we do know is that Mars has the ingredients: carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, all present in its rocks and soil. A history of liquid water, chemical energy sources, including perchlorates and iron compounds that some microorganisms on Earth are perfectly capable of using, and possibly liquid water in some form today. Radar data from the Mars Express orbiter suggested in 2018 the presence of a subglacial lake beneath the South Polar ice cap, possibly kept liquid by salts or geothermal heat. That finding has been contested. Some researchers argue the radar signature could be explained by other geological materials, and it hasn't been confirmed by independent instruments. The debate continues. Deeper below the surface, conditions might be more stable, shielded from radiation, with temperatures potentially above freezing in some regions. That's speculative, but it's speculation grounded in physical reasoning rather than wishful thinking. InSight, which operated from November 2018 until December 2022, studied Mars from the inside using a seismometer. It detected Marsquakes and helped constrain the size and state of the planet's core, which appears to be liquid, larger than expected, and less dense than models had predicted. That has implications for understanding why Mars lost its global magnetic field, which it once had. Without a strong field, solar wind gradually stripped away the upper atmosphere over billions of years. That atmospheric loss is itself part of the story of how Mars became the cold, dry world it is today. So the arc looks something like this. Mars started with the ingredients: water, energy, chemistry, time. Something changed. The magnetic field weakened, the atmosphere thinned, the surface dried out. We don't yet know whether life had time to get started before any of that happened, whether it retreated underground as conditions changed, or whether it never emerged at all. The sample return mission is the clearest path toward answering the astrobiological question with real rigor. Until those samples are on Earth and in laboratories, we're working with rover instruments that are impressive but limited. Mars isn't a solved problem. It's the most studied body in the solar system after Earth and the Moon, and its most important questions are still open. Next episode, we move to a very different kind of world. Part 8 looks at Jupiter, the giant that shapes the entire outer solar system. If you want to follow the full series from the beginning, the Mars playlist has every episode in order. Link in the description. And if this kind of careful, evidence-based look at the solar system is what you're here for, subscribing means you won't miss an episode. That is part 7 of Mars. Subscribe so you do not miss it.